네, 성진님 시작하시죠.
네, 시작하겠습니다.
네,
Hi everyone, this is TA Seongjin Park, and in practice 11, we will do the neural machine translation with the transformer, which you learned this week. So this is the table of contents. We first prepare the inputs, and then we will implement the transformer from very basic building blocks to the full transformer architecture. And then we will do train and evaluate the implemented transformer, and the final part is visualize the attention. So before we go, please press these two buttons here. It will automatically prepare the essential files and packages which is required to this practice. All right, I believe everyone pressed the button, so I will not gonna explain you the first part and third part because you already learned what is the neural machine translation and how to prepare the inputs for machine translation and train and evaluate the neural machine translation model. So yeah, this is just equivalent to the material you already covered in week 9. So I leave some reference links here. So if you have question about this part, you can go to one of this link and see the details. Okay, we will directly move to the second part, which is the implementation of transformer. So in practice week 11, we will learn how to implement the attention is all you need, which is written by Baswani in 2017. So this is the full architecture of transformer, and we will start from the very basic building blocks of the transformer. So in the first part, we will implement the building blocks of the transformer, which is the multi-head attention and position-wise fit for network and positional encoding. So in part A, you are going to implement the attention mechanism. So in this section, you will implement scaled dot product attention and multi-head attention. I prepare some images of the scaled dot product and multi-head attention. Sorry, multi-head attention and the query key value projection. So let's move to this part. Your first job is to implement the reshaping function, which is the input is the tensor in shape of batch size by sequence length by embedding dimension, and your output must be in the shape of batch size by number of attention head and by sequence length by head attention head dimension. This function is essential to some multi-head attention mechanism. So we will start with this reshaping function. So I will give 2 minutes to implement this function. If you have any question, feel free to ask me. Okay, let's start it. Okay, I will show you my own implementation. So I implement the reshaping function like this just by get the first two part of the shape tensor and then add the self number of head and the size of head dimension and reshape the function, reshape the input by this view function. And then finally, I do some permutation to match the shape like this. Okay, I think it's very simple example. So your next job is implementing the scale dot product, which you learned this week. And I prepared the picture of scale dot product. Your job is to implement this matrix multiplication function and the scaling function in here. I give you some basic steps to implement scale dot product. So I will give you 3 minutes to implement this function. Uh, you should aware that this is not the multi-head attention version. So you don't mind the multi-head this time. Uh, there's a question from Jiyun. What is the role of the star? I think the star in here is receiving the values from this new X shape. So yeah. Okay, I'll show you my own implementation. So we can do the matrix multiplication by the torch.matmul like this. And you need to transpose the last two dimension of the key, because you need to inner product the query and key. So you must transpose the last two dimension of key matrix, and then you divide the entire matrix by the square root of your embedding dimension. And this is just the optional part. This is the implementation of attention mask, which is uh, masking out the padding or masking out the some implement some causal mask, which is masking the future tokens, which is ahead itself. And then you can calculate the attention weights by softmax on these attention scores. And then you apply the dropout. Uh, Basically, this attention dropout is not appear in the paper, but if you see the implementation of attention is all you need, they also drop out the attention. So I add some dropout function after the attention score, but this is not the this is just the optional. So this is just the your design choice. All right, I believe everyone understand the implementation. And next part, we will implement the there's a question. So there's a question from Jiun. So attention props are attention output. All right. I missed the typing. This is typo. Yeah, you're right. The attention output is attention props. This is just a typo. Thank you for notice me. Yeah, so we implement the scale.product mechanism, and your next job is implementing the multiheadscale.product, which I prepared the picture and the equation here. So your input is query key value tensor and the attention mask, which masking out the attention, the position of the padding token or some causal mask. And your output must be the attention output, which is equivalent to the attention probability. And the attention weights the value of each attention. So, oh, right. Oh, sorry, I missed once again. As Yunsang said, it's right. So your Yeah, I believe this is the right form. So your attention probability must multiply to the value matrix. So these attention outputs are the attended features, and you also output the actual probability of attention. Sorry for confusion. So you need to do same thing in this function. So your output is the attended output. Attention output is the attended output, and the attention weights are the value and value or probability of each attention. So I give you 5 minutes to implement the multi-head scale dot product. You can follow this. I will copy this to the left side. Okay, I give you 5 minutes to implement the multi-head scale dot product. 어텐션 아웃풋 계산하실 때 value는 트랜스포즈를 안 하셔도 괜찮습니다. 어차피 값들이 곱해지는 것이기 때문에 혹시 트랜스포즈를 몇 번째 디멘전을 하시려고 하시는지 알 수 있을까요? 네, 이미 들어올 때 QK랑 같은 디멘전들이 다 맞춰져 있는 상태이기 때문에 따로 뭐 밸류는 트랜스포즈를 안 하셔도 됩니다. 아까 쿼리랑 키를 키를 so why do we transpose the key? Because we need to do the inner product and the shape of query key value is equivalent. So for the to do some inner product by using torch.metmol, you need to transpose the last two dimension. 그러니까 결국 어텐션 스코어를 계산하려면 내적을 해야 되고 내적을 하려고 그 킬의 마지막 두 차원을 지금 트랜스포즈를 해준 겁니다. 네, 감사합니다. Okay, I will show you my own implementation of multiheadscale.product. So this part is just same as the scale.product without the multi-head. And I add some attention masking mechanism. So if your self.causal option is turned on, then this tells you that the attention mask is the causal mask. So your attention mask, the shape of attention mask is something like sequence length by sequence length. So for the broadcasting, you need to unsqueeze the first and second dimension of the attention mask, which is the first dimension is the batch size, and sorry, second dimension is the side number of head, and then your only job is fill the attention weights by negative infinity, which is very large negative number at the position of this attention mask. And the other case, which is the attention mask is not the causal mask, which is the padding mask. So the job of padding mask is do not attend on the padding positions. So this padding mask is usually sizes batch size by sequence length. So in this case, for the broadcasting, you need to unsqueeze the first and second dimension of the attention mask, and then the only thing left is fill the attention weights with the negative infinite. Okay, so this is the how I implemented the attention mask, and the rest of part is bit same. You first do some softmax to calculate the attention score. There's question from Jaegyun. What is the causal environment? So okay, I'll show you example on the mm, Okay, so the difference between the non-causal and causal attention is in the causal attention, you cannot see the future tokens. For example, the current token is the this cat token, then you can only attend on the past, which is the D token here. So for calculate the attention score for this cat token, you can just attend on the D token and the cat token, and you cannot see the set on the met tokens in the future of the cat token. And in the perspective of the set token, you cannot see the on the met tokens in the future, and you can only see the past, the cat, and the set token itself. So this is the causal attention, and the bidirectional and or the non-causal attention is just there's no future and past that there's no future and past limitations. So the cat tokens can see all the tokens in the sequence like the set on the met. Okay. Okay, so back to the implementation. So to calculate the attention props, so you take the softmax on the last dimension and take the dropout on the probability matrix, but dropout is not the necessary, it's your design choice. And then to calculate the attended output, you take the matrix multiplication with the attention probability and the value matrix. And then you do some transpose on first and second dimension to use this at the encoder. So I believe the scale dot product mechanism have some errors because we will not use the scale dot product in the rest of part. So please refer to this multi-headscale dot product. Yeah. And you can see this concatenation because as you see here, you first concat the heads and then you project the concatenated heads to some output dimension. So this code do the concatenation of the heads, and then the below do some concatenation too, and then this line projects the attended output to output dimension. And then so you can get the attended output and the attention weights, which is the attention score or attention probability. If you have do you have any question about this implementation? contiguous가 무슨 역할이냐고 물어보셨는데 이거는 제가 잠시 기억이 안 나서 찾아보도록 하겠습니다. 이게 제가 돌리다가 에러가 나가지고 애드를 한 건데 이게 제가 so the option contiguous here is bit tricky, but its purpose is to allocate your tensors in some contiguous position in your actual CUDA or CPU memory. So If you do not do this contiguous, then your tensors are spread out in the memory of your computer. But if you add this contiguous line, then your tensors are allocated in some sequential or contiguous manner. So yeah, this is the uh, lore of this contiguous option. And there's a question from Rashida. Why is attention output permuted? Because oh, he already explained. So yeah, that's the purpose. So the permutation in this line is to concatenate the heads in single vector. Okay, I believe everyone understands the multi-head-scale dot product. And the rest of part is extremely simple. Just project the query key value vector into the query key value space by using this linear projection matrix. And as we implemented above, transpose QKV in some appropriate shape, and then do the scale dot product, and then you can get some scale dot product result. Okay, next we will implement the position-wise fit-for network. This is extremely simple, so I give you just 2 minutes to implement the position-wise fit-for network, which is just same as this equation. And I give you some basic building blocks here, and your job is to implement this equation in this to-do section with these building blocks. The B1 and B2 here is not the residual, it's the bias term, and W1 and W2 is the weight matrix. So there's no, the residual are not expressed in here, but yeah, you don't need to care residual. You can do some residual just like this. Okay, I will show you my implementation. This is extremely easy. So you can do the residual like this. First, save the input to some residual variable, and then you pass through these activations. So this is the layer projection, linear projection, and the ReLU activation, and you apply the dropout, and then you linearly project the output of this step once again, and then apply the dropout, and then you just add residual and the output of this to here, and this is the output of positionalized feed-forward network. Yeah, I believe everyone can easily do this. Okay, let's move to the sinusoidal positional encoding. So in this section, we will implement the sinusoidal positional encoding, which is just equivalent to this equation. I give you the basic form of this sinusoidal positional embedding. You do not need to care the rest of part. Your job is just implementing this equation into the to-do section. So I give you 2 minutes, and you can implement this part with NumPy or as your wish in torch tensors. All right, so what is the question? We first do the linear projection, and then we apply the ReLU activation, and then we apply the dropout. So I think the order is right. Yeah. So this line is just equivalent to, yeah. As Jong said, this line is just equivalent to the first do this linear mapping and then applying the activation on the linear mapped feature. So I do this for preventing the codes become too long, but you can do this in some divided manner. Okay, so I will first reply to Sojang. Why we add the residual? So when you see this picture, we implemented this part, and you can see there's a residual connection here. You can do you can implement the residual connection at the encoder part, but I implemented the residual connection in the feed-forward network. So we will not gonna do residual network at the encoder layer, but I think it's just the design choice. So you can do the residual connection at the encoder, not in the feed-forward network. And so I think Jung already replied to Jaewon's question. Yeah, you can find some details on the torch documentation implementation and the very first part of our lecture. Okay, I will show you the sinusoidal positional encoding. So I implemented the sinusoidal encoding like this, just following this equation. I used the NumPy, but you can use any other math library to calculate this value. I think this code and equations are trivial, so I will move on to the next part. So in part one, we implemented the basic building blocks. So in part two, we will implement the encoder part of the transformer. Let's do, there's a question from Mario. EI입니다. 여기 보시면 EI가 있어서 E 곱하기 I 하시면 됩니다. 이 이퀘이션 그대로 어떤 거 말씀하시는 거죠? 아, 맞네요. 죄송합니다. 여기에 이걸 했어야 됐는데 제가 까먹었네요. Yeah, I made some mistake. So you need to do something like this. 그렇네요. 네, 맞습니다. 이렇게 하시면 될 것 같습니다. 네네, 제가 이거를 해놓고 까먹고 있었네요. 네. So I increase in range 2. So your implementation was like this. Thank you for the correction. So why we do the detach here? Yeah, we this sinusoidal position and embedding is not trainable. It's fixed. And so 네, 학습 안 하려고 그냥 디태치를 하는 겁니다. 사이누소이달 포지션 임베딩은 학습이 진행된다고 해서 업데이트를 하지 않을 거기 때문에 여기서 디태치를 하고 갑니다. Thank you. Okay, I'll move to the encoder part. So in part A, you will implement the encoder layer, which is this gray colored block in this picture. And I give you some basic building blocks here, and your job is to implement the rest of part. I will give you 5 minutes to implement the transformer encoder. Okay, I will show you my own implementation. So I implemented this gray block like this. As we done in position-wise fit-for network, we first set the residual variable and pass the input to self-attention layer, which we implemented in part 1. And then we get the attended outputs and attention weights, and we apply the dropout on the attended output, and then we add residual and the X to get the output of this add part. And then we apply the layer norm top of this X to get this yellow block. And we move to the position-wise fit for network. And we already implemented the residual connection in here. So there's no residuals in this encoder, but you can do the residual connection in encoder, and you can remove the residual connection from the position-wise fit for network. It's just the design choice. And then you apply the top of fit for network. You apply the layer norm on the top of fit for network. And then you will return the final output of the layer and attention weight. This clamping is just limit the value of the matrix to do not explode. So you can just remove this one, but many of the some transformers packages are using this clamping. So I believe this is just the design choice, but I recommend to contain this line in your encoder. So do you have any question about the implementation? Okay, I will move to the second part, which is the implementation of the full encoder. Your job is to stack the encoder layers and build the full transformer encoder. We will bring the encoder layer, which we implemented above here, and I give you some basic building blocks once again. And your job is to build encoder, which is same as this full picture. In the encoder, you must convert the input integer sequence into the input embedding and positional encoding, and then pass these embedded inputs through the n repetition of the encoder layer. So I give you 5 minutes to implement this encoder. 혹시 이 라인을 말씀하시는 게 맞으신가요? 요 라인 말씀하시는 건가요? 네, 이게 이 X의 데이터 타입에서 가질 수 있는 가장 큰 값에서 1000을 빼준다는 의미입니다. 이게 이렇게 하지 않으면은 네네네. 네. So I see you the architecture. There's a question from Mario. Why we didn't do the residual connection after the position-wise feed-forward network? Because we already implemented the residual inside the position-wise feed-forward, so yeah, you don't need to do once again. But 네. 이건 그냥 저의 구현일 뿐이지 조금 더 명확하게 하시려면은 이 포지션 와이즈 피드 포워드에서 레지듀어를 꺼내시고 이 인코더 단에서 레지듀어를 구현하시는 것도 괜찮습니다. 근데 저는 이렇게 한 이유는 그렇게 하면은 나중에 코드가 너무 길어져서 뭔가 보시기 힘들까 봐 안에 그냥 넣어 버렸고요. 네, 그런데 이렇게 하나 저렇게 하나 선택이시니까 편한 방향으로 하시면 될 것 같습니다. 그 위쪽 구현에 포함되어 있다는 게 혹시 어떤 의미인지 좀 더 자세하게 설명해 주실 수 있으신가요? There's no residual connection in the implementation of multi-head attention, so you need to do the residual connection outside of the multi-head attention, like this one. 네, 감사합니다. Okay, I'll show you my own implementation of the full encoder. It's very simple. You just pass the integer input ID sequence to the token embeddings and the positional embedding, and then just add 2 to get the input feature. And then you apply the dropout once again here. And then the rest of thing is just pass your input feature sequentially through the encoder layer, which you implemented above. So I use the for loop here. So the set layers is this module list in this line. And then this will returns the n repetition of this block. Oh, I believe that's just the design choice. And as you can see here, you can concat the positional encoding and input embedding, and or just adding them. But nowadays, more user case is just adding two embeddings. So it's okay to concat the embedding, positional embedding and input embedding, but the drawback of concatenation is it increases the input hidden dimension by 2. So the number of parameters and the vectors are become more larger than just adding them. So I recommend to just add input embedding and the positional embedding. Do you have any other question? 더해줘도 상관이 없습니다. 어차피 매트릭스 멀티플리케이션 하고 뭐 레지덜 커넥션으로 계속 입력이 올라가기 때문에 뭐 더하거나 그 컨캣 한다고 해서 크게 차이는 없고요. 저는 컨캣을 하면 오히려 그 디멘전이 2배가 되기 때문에 그것 때문에 학습이 더, 만약에 가지신 샘플이 적다는 가정하에 디멘전이 늘어나는 게 훨씬 악영향을 줄 가능성이 크므로 그냥 더해지는 게 더 자연스러운 폼이다라고 저는 생각을 합니다. There's a question from Rashida. How is n repetition implemented in your code? So you can see the for loops here. And these self layers contains the n repetition of the encoder layer. And our job is just passing the input features to n times in just like this. And the number n is expressed in here. Set range config.encoder layers. Oh, thank you. Okay, I believe we can move to the decoder part. The third section is the Transformer Decoder. So in part A, you will implement the decoder layer, which is just this grayish block here, not the n repetition. So just like the encoder layer, you using these building blocks here, and your job is to implement that single block of the decoder. By the way, there's two masking tensors are here. Causal mask is for the decoder self. This causal mask is for the decoder self attention, and this encoder attention mask is for the encoder decoder attention to avoid decoder attend on the padding tokens on the encoder. Okay, I give you 5 minutes to implement the decoder layer. If you have a question, please ask to me. I will show you the architecture of decoder layer. The two thing is different from the encoder. There's a cursor mask in the lower this part, and then your model must attend on the encoder hidden states in this part. This is my own implementation of the decoder layer, which is very similar to the encoder part. So we first do the residual connection, which in here. And then we do the same self-attention. But you need to aware is having this kind of the attention mask, which is the causal mask. So okay. So you do the self-attention with causal mask and then apply the dropout and then do the residual connection and then apply layer num. And then we do the cross attention block here by setting query as the X, but the key is now the output of the encoder. So you set the key as an output of the encoder, and we just apply the encoder padding mask here, and you get the output, and the rest of the part is same as the upper. And then this is same as the position-wise fit for network as we seen before. And yeah, that's all. I think this is very similar to the encoder part, but I think I mistake something here because yeah, I didn't make a mistake. You should turn on the causal option to successfully add the causal attention mask to your decoder self-attention layer module. Okay, do you have any question about the decoder implementation? Okay, let's move to the decoder implementation. Implementation 여기는 so why there is no clamping here? Because the gradients are stacks over and over, and if the layers are placed in the low level or low abstraction level, then the gradient accumulation is becoming bigger and bigger. So you can do the clamp on the entire of the transformer architecture, but in this case, maybe the gradient exploding is only occur in the encoder layer. So the people try to clamp only the encoder part, but you can clamp the decoder part for the safety. Yeah, that's right. 네. 클램프 같은 거는 아까도 말씀드렸듯이 디자인 초이스이기 때문에 여기서 하셔도 되고 아예 인코더에서 떼셔도 되는데 그냥 인코더, 디코더 전부에서 클램프를 하는 게 나을 것 같습니다. Okay, so I just show you the decoder implementation because this is just equivalent to the encoder implementation. So you can see the equivalent embedding process and then apply dropout, and then you can do the same thing just like the encoder. You doing some for loops by applying the for loop, we can do the n repetition of the decoder layer. I will give you 1 minute to receive question and move to the next part, which combine the encoder and decoder in one place. Okay, let's move to the transformer. For transformer, oh, there's a question. What is the cross attention scores? This is equivalent to the encoder decoder attention score. Some people say this as a cross attention score. The reason why we keep this attention score is because we will use this output, these attention scores at the visualization step. So we keep the attention score from each decoding layer for visualization purpose. And the cross attention is just same as the encoder decoder attention in here. Okay, let's move to the transformer part. The last implementation practice is generating the mask for encoder and decoder attention. So input is the source and target sequence in your machine translation dataset, and your job is to return the encoder attention mask, which is masking out the padding tokens in the encoder input, and then the decoder attention mask is the cursor mask for the decoder. So I give you 2 minutes to implement this generate mask function. Okay, I will show you my own implementation. I implement the attention mask like this. For the encoder padding mask, uh, first we get the ID of padding token and uh, find the position of the padding token in the source source, and then we do this by we mark the position of the padding token by using torchjump equal, which is make true to the position has same value as like this, and false, which is the mark as which is marked as 0 when the value is not matching with this. And I implement the causal mask like this. Your causal mask should be in lower triangular matrix. So first I made the tensor, which is filled with the true value, and then I made some sequential list with the from 0 to the length of the target sequence, and then just mask fill the false with this A range. So after this 3 line, your attention mask tensor will be in form of the lower triangular matrix. Yeah, I believe everyone can easily understand the code. And the rest of the part is extremely simple because we first generate the mask for encoder and decoder and just pass the encoder mask and decoder mask to the encoder and decoder, and also pass the input to the encoder and decoder. So I will pass this step, and I wrote down the configuration to which is needed to train and evaluate your model. You can modify one of the hyperparameters when your training or evaluation is not successful. I believe everyone is familiar which one is the each line, meaning of each line. And I also skipped the training and evaluation step because you already learn how to train and evaluate the machine translation models in week 9. So I believe this is not helps you anymore. Okay, maybe in Colab, your model takes 20 seconds per epoch, and yeah, it takes 20 seconds. So it's not enough to check the output in this practice session. So I will directly show you the visualization and the positional embedding. There's some mistake in my positional encoding. So this is not the equivalent to the correct form, but the visualization of positional embedding is something like this, like some sinusoidal forms exist in the positional embedding, and you can check the form of the positional embedding in this part. And I bring some visualization tool here, and you can check the attention. You can visualize the attention in here. You don't need to change these 2 lines, and your only job is to change this final block of your code. And when you run this code, then you can see the visualization of your attention like this. But I think I have a mistake on implementing the positional embedding. So the result is not that correct, but you can see how the English tokens are attending on the German tokens in the German sentence. So I believe this will help you to implement and analyze your model in qualitative manner. Yeah, I think everything is explained. So do you have any question about this practice, or I'll end the practice week 11?
네, 성진님 감사합니다.
네, 감사합니다.
네, 그러면 thank you very much all, and I'll see you guys next Tuesday. Bye bye.
감사합니다.
네.